Welcome, this is Dr. Plague, and this will be the last video on the Plague Mark I homemade CPU before moving on to the Plague Mark II, which will add a lot more functionality compared to the Mark I. If you will remember from part 1, I first built up a version of the Plague Mark I which did not work correctly, at least with the Atmel flash chip. The first version used a 74393 binary ripple counter, and I've rebuilt that version right here. In the last video, we changed out the 393 counter to a different counter to get it to work. In this video, we're going to explore some ways to get the 393 to work in the Plague Mark I CPU. Before we make any changes, let's take a closer look at why this version is failing. I'm going to connect it up to my Regal scope on that bench over there. That will allow me to use the Logic Analyzer functionality to help examine the issue. Since I won't be next to my OWAN waveform generator back here, I'll just use the waveform generator output from the Regal scope to provide a 5 Hz square wave to the CPU. First, I'll connect up the 4-bit binary counter output to the Logic Analyzer probe. Then, connect the reset line coming from the most significant data line of the flash chip up to analog channel 1 of the scope. I'll apply power, then turn on the 5 Hz square wave and trigger off the reset line. Perfect. Let's see what we've got here. Now, this red trace down here represents the least significant binary digit of the counter, and then moving on up to the green traces, we see the second least significant digit, then the third, and finally the most significant digit of the binary counter. This grayed out area right here shows the decimal value of the binary counter at any point in time. Then, the yellow trace shows the signal coming from the flash chip to the reset pin of the counter. Ideally, with the first code we wrote in part 1, which resides in the flash chip, the counter should count from 0 to 11. Then, on count 12, it should reset back to 0. But what happened here is that the counter counted from 0 to 7, then on count 8, it reset back to 0. And we can see the reset line glitched up a little bit right here, which caused the erroneous reset on count 8. We can also see an issue right here due to the ripple counter. Between the counts of 7 and 8, we can see the count transitioned to 6, 4, and 0 before landing on 8. Because the 393 is a ripple counter, there will be a propagation delay from one bit to the next as the counter changes value. The propagation delays will start with the least significant bit and work its way up to the most significant bit, as we can see here. We're getting about 6 to 7 nanoseconds between each output bit, and that's what accounts for the 6, 4, and 0. Even if we were to use a synchronous counter, we still can't be guaranteed that all the bits will change at exactly the same time. The changes would be much closer together, but if we kept on zooming in, we would find that they are not perfectly simultaneously changing. One of the best ways to combat changing from one count to another is to use gray code. If you're not familiar with gray code, it is just a method of counting in which we use non-sequential numbers that change by only one binary bit at a time. To determine the gray code counting sequence, we can use the reflection method. So we start with a 1-bit counter that counts from 0 to 1. Then reflect that about this horizontal line, and add another bit to the left, with zeros above the reflection line and ones below it. Then repeat for additional bits. We can see that moving from any one number to the next in gray code only requires changing one bit. Now, obviously, the 393 counter is not capable in and of itself of counting in gray code, so I won't be using that method in this video. I will come back to gray code in some future videos, but for now, let's find another solution. The 393 increments its count whenever the clock line transitions from a high to a low. So let me draw this up here. Let's say this is the clock signal, and here are the counter values. we can see that at each of the clock's falling edges the counter increments. And on the rising edges here, the counter value is stable. So it might behoove us to only capture the counter value when it is stable. What we could do is use a series of D-type flip-flops to store the counter value during each rising edge. We could use a 74-273 IC, which has 8 D-type flip-flops. These flip-flops will store the input values on each rising edge of the clock signal. So let's take our original circuit here in DigitalWorks and add in a 74-273 between the memory outputs and their destinations. And of course, we need to pull the reset line of the 273 high for it to work. We also need to connect the clock signal to the clocking pin on the 273. Now let's give this a go. It does work, except when we get to the reset instruction. Remember in part 1 where we had to add the LED output to the reset instruction? Well, we would need to do the same thing here, except the opcodes haven't switched like they did in part 1. But what if we don't want to change the instructions? What if we want this CPU to work without altering the code in the flash chip? What if we want the asynchronous reset instruction that we had originally? We could try to do it using a transparent latch, like the 74-373. The pinout is almost identical to the 74-273, except its reset line is replaced with an output enable, which now needs to be low. Also, the clock pin is now renamed to latch enable. With this chip, the D latches will only store the input values when the clock signal is low, and the outputs will follow the inputs when the clock is high. If we look back at the plague board, we can see that the count only starts transitioning to the next value when the clock signal goes low. Therefore, if we store the counter value when the clock signal first goes low, we will never see the transitioning process and we should get a clean value from the flash chip. Okay, let's try this one out. And now it works just fine. So, let's take a quick look at what we had in the first video. We had a counter connected to a memory chip. And this is what I considered to be the CPU. I had a clock coming into it, then it had 4 address lines, and 1 data line connected to it. It had an instruction to output data to some LEDs, but that output did not come from the CPU. It came directly from the memory chip, which is external to the CPU. This is not what we would expect from a traditional CPU. But what we did so far in this video is to add in an 8-bit D-type latch. Now we have a clock line, 4 address lines, 8 data lines, and a 7-bit output port. All the data lines from the memory chip come into the CPU, and the out instruction has its own port on the CPU to send data out. This is starting to look more like a traditional CPU, but we are still far from it. So let's add the 373 chip on the breadboard and verify that this actually works outside of a simulation. I'm starting with the version that did not work, and I'll power it on to prove it. Okay, let's add in the 373 chip, along with power and ground. Then I'll pull the output enable pin of the 373 low. Now, remember that this 74541 chip is only used to buffer the output to the LEDs, and everything up here is external to the CPU, and the CPU is all contained on this lower breadboard. I'll remove all the data lines from the flash chip to the LED buffer, that is D0 through D6. And I'll remove the data line from the flash chip to the reset of the counter chip, D7. Next, I'll connect all the flash data lines up to the 8 inputs on the 373 chip. I'll connect the first 7 outputs from the 373 chip up to the LED buffer. Then I'll connect the last output from the 373 chip up to the reset pin of the counter. Lastly, I'll connect the clock signal going into the counter up to the latch enable pin of the 373. Now, let's power this up and add the clock signal. And voila! It now works with the Atmel flash chip. Now, even though it does work, I still don't like it, because it is asynchronous. I prefer all CPU instructions to be synchronous. That way, we should always know when the instructions will execute and how long they will take to execute. When our reset instruction executes asynchronously, it will appear to execute instantaneously, but we should all know by now that that doesn't happen in real life. There are propagation delays that we will see if we single trigger on the reset line. The 7 LEDs 0 through 6 are shown below. Then we have the reset line. The clock is next. Then, up here, we have the address lines from the counter and their decimal values shown in the gray area below them. After the clock goes high, it takes about 16 nanoseconds for the 373 to latch. Then we can see the reset line go high while LED 1 turns off. The reset line resets the counter providing the address from 12 to 0, and that takes about 6 to 7 nanoseconds. This new address of 0 accesses an instruction from the flash chip to turn on LED 0, and that takes about 55 nanoseconds, which is actually pretty impressive since this Atmel chip is only rated for 70 nanoseconds. Anyway, we can see the execution of the reset instruction was not instantaneous. It took about 61 to 62 nanoseconds to fully execute. So, based on that, I would prefer to use the 273 over the 373 and just add in the LED output to the reset instruction. Now, let's change the code in the flash chip to match the code in DigitalWorks. And let's replace the 373 with the 273 and test this out. But before we power this up, we need to pull the reset line on the 273 high. Okay, let's give it a go. Looks good. Now, there's one more solution that I'd like to present in this video, and that is to use a method known as strobing. This is similar to a strobe light, the type of light that flashes on and off. It strobes. That's what this method is doing. It strobes the output. It turns the output on and off. Specifically, it'll turn the output off during any potential periods of glitching and only allow stable outputs to get through. For an example, let's take a look at this old college textbook of mine. Now, the title here mentions VHDL, but in the class that I used this in, we did not use VHDL. Instead, we just used 74 series logic, so this book can apply to logic in general. Actually, we used Verilog in college, not VHDL, but we didn't start that until some later classes. Now, let's look on this page here. It shows something similar to what we have. A counter here driven by a clock signal, and a decoder chip which we could compare to our flash memory chip. We send in a value or address to the decoder, and we get some type of data out of it, much like with our flash memory chip. The big difference here is that this counter is positive edge triggered, while our counter is negative edge triggered. Otherwise, it's the same concept. We'll just need to flip the edge triggering in our design. If we look at the outputs down here, this appears to be a ripple counter just like in our design. The changes ripple through the bits, and this is what causes glitching in the decoder outputs. Now, in our case, the glitching may not be just from the ripple effect, but also from just changing the addresses going to the flash chip. Nonetheless, there is still glitching on the outputs. So, on the next page here, they show how we can use a strobe line, which in this case is actually the same as the clock line. You can see here that when the strobe line goes low, the output from the decoder is allowed to pass through. If we go back to this page, we can see that the glitches only occurred after the clock transitioned from a low to a high, so there is no glitching when the clock is low. Therefore, we disable the output when the clock is high. The output is only sent through part of the time. In other words, it is strobed. We make sure the output is disabled only during the time periods that glitching can occur, and we enable the outputs when they are stable. Now, as I mentioned, this counter uses a positive clock edge, and our counter uses a negative clock edge. Therefore, we want to do the opposite, and have our output enabled only when the clock is high, and disable it when the clock is low. In the book, there is an enable pin on the decoder, which only enables it when the input is low. But since we're doing the opposite, we need to find a way to enable the output when the clock is high. What we're looking to do is only allow our reset signal to pass through when the clock is high, and we want the reset signal disabled when the clock is low. And in our case, a disabled reset signal is a low signal, since the 393 counter resets when the reset pin is high. So let's draw up a truth table here. We have our clock signal and reset signal coming from D7 as the inputs, with the output being the new reset signal. And there are 4 combinations of logic levels here. Whenever the clock is low, we want to disable the output. In other words, set it to a low. And when the clock is high, we want the output to be equal to D7. Now, if we look at this table, we can see that the only time the output goes high is when both of the inputs are high, which is the behavior of an AND gate. Therefore, starting with the original design, I'll just throw an AND gate in here like this. I'm using the clock and the opcode bit as the inputs to the AND gate, and I'm sending its output to the reset pin of the counter. I have the original code from the first design programmed into the memory chip. And if we run this, we can see a little glitch in the output during the reset instruction. This is because the reset opcode does not get to the counter during the first half of the clock cycle when it's low. Let me single step through this to show you. The clock is low, and the reset did not get through to pin 2. Now, if I step one more time, we can see that the counter immediately resets back to 0, and we get the LED output from the first instruction. To fix this, we could add in the LED output to the reset instruction, but this time we would want the same output as the first instruction we're resetting back to, which is a 1. So let's add an output of a 1 to the reset instruction and rerun this. Now it works fine. FYI, you'll notice that I only strobed the opcode and not the operand, and this is for an obvious reason. I don't want strobe lights. Let's program this code into the flash chip and breadboard this up. Now, I've rebuilt the circuit I started out with at the beginning of this video. I'll use a 74HCT08 quad 2-input AND gate IC and connect power and ground. I'll be using just the first AND gate, and I'll terminate the other AND gate's inputs to either power or ground. I'll connect the most significant data line to one input of the AND gate, and the clock to the other input. Then I'll connect the output of the AND gate to the reset pin of the counter, and the moment of truth. Excellent! We can see that this version works too. Now, to be honest, I would not use strobing in this fashion. With this solution, there would be little consistency with the number of clock cycles a particular instruction would take to execute. For example, after a reset instruction, a following out instruction executes in only 1/2 a clock cycle, whereas normally the out instruction takes a full clock cycle. This is because in this case, the signal we are strobing is actually affecting the signal that is being strobed. So this is just a bad solution, and I would avoid it. Now, there are situations where strobing could work properly, and I will be using strobing in some future videos. So, because of that, I wanted to introduce the idea even though it doesn't work well in this situation. Now, realistically, I would not use a 393 counter in a CPU to hold the instruction pointer, mainly because we cannot preset the value to any arbitrary value. We can only increment it or reset it back to 0. This means that we cannot use any type of jump instructions with this type of counter, unless it's only to jump back to 0. But these types of counters will have their place in some future videos that I will be creating, specifically for projects that I want to add in a mini CPU that doesn't require any jumps. And when I place these little mini CPUs inside future projects, I will generally refer to the code that they run as microcode, which is basically an embedded program that sequences the control of hardware within a circuit or IC. We'll talk more about that in future videos. Well, that wraps up the Plague Mark I homemade CPU. And next, we'll be moving on to the Plague Mark II in some future videos. That's not to say I won't come back to the Plague Mark I. It's unlikely, but it could happen. So, let's talk about what are some of the takeaways from the Plague Mark I. Well, obviously it's not very useful unless you want to sequence some LEDs. But the big idea that the Plague Mark I shows us is how we can get a CPU to follow a set of instructions in a sequential order. We also looked at some ways to change the value of the instruction pointer, and even created a working jump instruction. These are fundamental ideas that can be used in the development of future CPUs. The Plague Mark II homemade CPU, which I'll be designing next, will expand upon these ideas and give us much more control with the programs that we write. And since the number of CPU instructions will start growing, we'll also start looking into designing a very simple assembler, so we don't drive ourselves batty with assembling our own code. Well, that's it for this video. I hope you've enjoyed it, and I'll see you next time, right here on Dr. Plague.